Learners and viewers, welcome to the session for quantitative analysis for managerial application MLTC 005. Today, we will be discussing about four measures of variation and skewness. We have already discussed the previous sessions that what is data, what are the different types of data, how data are presented, how evaluation processes work, that is how we mean mode, median, modes of. Now, what is their application? So we will start with significance of measuring variation. Measuring variation is significant for some of the following purposes. Measuring variability determines the reliability of an average by pointing out as to how far an average is representative of the entire data. Another purpose of measuring variability is to determine the nature and cause in order to control the variation itself. Third one is measure of variation enables comparison of two or more distributions with regard to their variability. What are the properties of a good measure of variation? A good measure of variation should possess, as far as possible, the same properties as those of good measure of central tendency. Following are some of the well-known measures of variation which provide a numerical index to the variability of the given data. First one is range, second is average or mean deviation, third one is quartile deviation or semi-interquartile range, and the fourth one is the most important part, that is the standard deviation. Mathematically, first we will see about their theory, then we will see how it is evaluated through one numerical. What is absolute and relative measure of variation? Measures of variation may be either absolute or relative. Measures of absolute variation are expressed in terms of variability. And in case of two or more data are expressed in different units of measurement, then the absolute measure of variations are not compared. That means we cannot compare kilometers with kg. In such cases, measure of relative variation should be used. The another type of comparison for which measure of relative variations are used, it involves the comparison between two sets of data having same units of measurement but with different means. We'll start with range. Range is the difference between the highest and the lowest value of the distribution. Suppose we have an example of 2, 3, 4, 5, 6, 7, 8, 9, 10. So the lowest number is 2 and the highest one is 10. The difference of 10 and 2 is 8. That means the range is 8. The range is the simplest measure of variability to compute. However, it does not use all the numbers of the data. As the sample size increases, the range can increase, but the range can never decrease. For example, number is 2, 3, 5, 10, range is 8, and the numbers have increased from 2 to 10 now. So again, the range is 8. The range does not give any information about the nature of distribution of the values. Irrespective, they can be of in any form. What is the coefficient of range? That is the highest minus lowest to highest plus the lowest. Then comes quartile deviation. The quartile deviation, which is also known as semi-interquartile range, is computed by taking the average difference between the third quartile and the first quartile. That is, QD is equal to Q3 minus Q1 by 2, where Q3 is the third quartile and Q1 is the first quartile. And the relative measure corresponding to quartile deviation is known as coefficient of quartile deviation, which is evaluated as Q3 minus Q1 by Q3 plus Q. The quartile deviation is superior to the range as it is not based on two extreme values, but rather on middle 50% of the range. That means Q1 is 25% and Q3 is 75%. So we are talking about the difference of 50% of the data. Another advantage of quartile deviation is that it is the only measure of variability which can be used for open-end history. The disadvantage of quartile deviation is that it ignores the first and the last 25% of the output. Then comes average deviation. The measure of average deviation is an improvement over the previous two measures as that it considers all observations in the given set of the data. This measure is computed as the mean of deviation from the mean or from the mean. All the deviations are treated as positive regardless of the sign. That is why you can see that different after summation we have used mod sign. That means the difference of x minus x plus, whether it is plus or it is minus, it will remain positive divided by n. That is, if we are talking in terms of mean, it will be x minus x bar. And if we are evaluating in terms of median, it will be x minus median by n. In both the cases, the number will be a positive. There is an advantage in taking the deviations from median because the sum of the absolute deviation from median is median. In actual practice, however, arithmetic mean is more popularly used in computation of the average deviation. The relative measure corresponding to the average deviation is called as coefficient of average deviation. Average deviation can be computed from median. The coefficient of average deviation shall be obtained by dividing the average deviation by median. If we are considering median, so average deviation will be divided by median. And if we are evaluating in terms of mean, it will be average deviation divided by median. Although the average deviation is a good measure of variability and its use is limited. If one desires only to measure and compare variability among several sets of data, the average deviation will be used. The major disadvantage of average deviation is that it lacks of mathematical properties. It is truer because non-use of sign in it makes it algebraically inconsistent. Now, this one is the most important part, that is standard deviation and variance. Standard deviation and variance measures variability about the standard deviation is used in other statistics and it is the most stable of the variability indices. If one reports the mean as the measure of central tendency, then standard deviation is also reported. Standard deviation is good for interval or ratio data. However, the standard deviation is affected by extreme variance. Approximately 68% of the measurements will fall within one deviation of mean. 95% will fall in two standard deviations, and 97.7, that is almost 100%, fall within the three standard deviations. The concept of standard deviation was introduced by Carl Pearson in 1893. Now, because we are talking about mathematical, so first of all, we have to know what are the mathematical relations. Depending upon the data available to us, we have seen it how the mean is evaluated. When the data, there are three types of data. Depending upon the nature of the data, the formulas are used. Similarly, here, so if we have n individual concentrations, in that case, standard deviation will be under root of summation of x minus x bar whole square divided by n. You have to be very careful. Don't remove this square by the under. This is what we will be evaluating. We will see how it is evaluated. And for group data frequency, that means if frequency is given to us, it will be summation of f and x minus x bar whole square divided by n. If the data is and we are using deviation or we are using assumed, in that case, the formula will become summation under root fd square upon n minus summation fd by n whole square into I. I is outside the under root. where D is equal to X minus A upon Y. Similarly, what we have used in evaluation of variance being the square of standard deviation, it is denoted by sigma square. So variance is equal to sigma square. Now we will see how mathematically mean and standard deviation are evaluated. We have been given this data about for library membership of children in different ages. We have to find the mean and standard deviation of the memberships. What we will do? We will pick up the data. 3 columns are given to us. So for the age group, first column will be for the age group, second will be the membership fee, and third will be the number of students. From there, we will be evaluating FX and FX. We will represent membership fee at X and number of children, that is F, that is frequency. After multiplying, we will get FX as 30 into 110, which becomes 300, and FX square. We have to square 30. 30 square is 9. 900 into 10 is 9. So similarly, we will be evaluating for all the groups. And we have to sum. Sum of the frequency will be 30. Sum of FX is 1290. And the summation of FX square is 59900. First, we have to evaluate the mean. Mean is summation of FX divided by 30. That means 1290 divided by 30, which comes out to be 40. The mean is 40. Now we have to evaluate standard deviation. So we will be using the relation because we have frequency with us. So we will be using the formula under root FX square by we have to see the standard deviation. Largest the standard deviation, greatest is the mean. But when considering distribution with different means, decision makers can't compare the uncertainty in distribution only by comparing standard deviations. In this case, the coefficient of variation is used. That is, the coefficient of variation for different distributions are compared, and the distribution with the largest coefficient of variation has the greatest relative variation. Now the question arises, how we will evaluate coefficient of variation. Coefficient is denoted by Cv, which is equal to sigma upon sigma times d divided by x bar into. Then comes skewness and convergence. Skewness refers to asymmetry of the distribution. That means variation from the mean point. Symmetry means that for a given deviation from the central value, there are equal number of observations on either side. That means we can say that 50% on the left side and 50% on the right side. If a distribution is skewed, it will have a longer tail either towards left or towards right. Thus, skewness is departure from symmetry. In a symmetrical distribution, mean, median, and mode are equal. This is one of the most important parts of it. Remember, in symmetrical distribution, mean, median, and mode, all the three values are equal. If a distribution has long right tail, it is positively skewed, and if it has long left tail, it is negatively skewed. Now we will see. Here you can see if mean is the greatest and mode is the smallest. lowest, and median is in between. It is positively skewed. And if mode is the greatest and the mean is the lowest, it is negatively skewed. In the center one, you can see it is a bell-shaped, symmetrical, 50% on left, 50% on right. Rather. In that case, we can say that mean, median, mode, all the three are equal. Now, what is coefficient of skewness? This was proposed by Carl Pearson, and it is based on mean, median. If we talk about coefficient of skewness, it is denoted by xk, which is equal to x minus mean minus mode upon standard deviation, which is again equal to mean minus mode upon standard deviation. And if it comes in top in terms of quantile, it is Q3 plus Q1 minus 2 times of Q2 divided by Q3 minus Q2. You remember that we have an empirical relation, but we can convert that, this mean minus mode, in terms of mean and median. That is 3 times of mean minus median upon standard deviation. Now, depending upon the value of SK, that is coefficient of skewness, we can determine whether the data is positively skewed, negatively skewed, or symmetrical. If SK is greater than 0, it is positively skewed. If SK is less than 0, it is negatively skewed. And if SK is equal to 0, it is symmetrical. From the data, from the interpretation, what we evaluate, there we can decide. Bode proposed a relation, that is Q3 plus Q1 minus 2 times of median divided by Q3 minus Q. Now we will evaluate and see whether there is any difference between Carl Pearson formula and Bode's method for evaluation of coefficient of skewness. The data is given to us. We will start the evaluation. Column number 1 and column number 3 was given to us. First of all, we have to find out the mid values. Mid value will be 10 plus 12 divided by 2, which comes out to be 11. You can see that there is a difference of 2. Simultaneously, we will be adding 11 plus 2, 13, 13 plus 2, 15, till 23. At the center of the data, which has been marked as with red box, 3 terms are above it and 3 are below. So we will be assuming this mid value as 7. Now, column number 4. We have to evaluate D is equal to x minus 17 divided by 2. That is, if you remember the formula, D is equal to x minus a upon. So I is the difference between 12 and 10, that is 2. X is the value of mid value, and 17 is what we have SU. Right. The column where we have assumed, we can straight away write 0. Above it, we can write minus 1, minus 2, minus 3. And below 0, we can write 1, 2, 3. Now we have to multiply FD. FD will be 3 into minus 2, that is minus 21. FD square, that will be a positive number. D is minus 3, its square will be 9. 9 into 7 is 63. So similarly, we will be evaluating all these terms. And we will find N as 100, summation of FD as minus 9, and summation of FD square as 250. First of all, we have to evaluate the mean. Mean x bar is equal to A plus summation FD upon N into I. Your A is 70, your summation FD is minus 9, your N is 100, and I is 2. After evaluation, you can find it is mean. Its mean is equal to 16.8. Now we will evaluate mode. Mode is equal to L plus D1 upon D1 plus D2 into I. That comes out to be 18.5. Now we have to evaluate standard deviation. Standard deviation is summation of D square upon N minus summation FD upon n whole square into n. All the values have been evaluated over here. We will just place them in the formula. And after that, we will get standard deviation as 3.1634. Now we will evaluate this, that is coefficient of skewness. We have evaluated, since we have evaluated mean, mode, and standard deviation. So we have a relation mean minus mode upon standard deviation. After evaluation, we get that its value is negative 0.5310. Now, what will be the interpretation? This value of coefficient of skewness indicates that the distribution is negatively skewed with the negative sign, and hence there is a greater concentration towards the higher profits. Now, block 2, that is related to probability and probability distribution. There are 4 units in it. Basic concept of probability, discrete probability distribution, continuous probability distribution, and the decision theory. We will start with the basic concept of probability. The probability is concerned with random experiments, data, demands, and interface to be drawn, and statistical inferences are never certain. Statisticians would be prompted to use prefixes or suffix as likely or at most likely. Prediction, we may say that tomorrow it may rain. Tomorrow it will rain. Nobody can say, but it may rain. That is what we have. A probability. Probability and its concept are thus very important to interpret the inferential statistics. The theory of probability is a study of random experiments. In a random experiment, set of all possible outcomes is always known, but it is not possible to predetermine the outcome. For example, the probability of a coin toss results in either heads or tails. Is the probability of a coin toss resulting in head is because the toss is equally as likely to result in tails, and there are 2 possible outcomes when we are going to toss a coin, either head or tail. Basic formula for probability is number of favorable cases upon total. Favorable case for head is 1, either head or tail will come, and the total number of cases is 2. That means if we talk for the probability of head in a single toss of a coin, we will say that the probability of getting head will be 1 by 10. Similarly, for the probability of getting tail will be 1 by 10, which is 0.5. Probability deals with calculating the likelihood of a given event's occurrence, which is expressed as a number between 0 and 1. An event with probability of 1 can be considered as a certain event, and an event with a probability of 0 can be considered as an impossible event. Now the thing is that tomorrow sun will come. It is, everybody knows will come. But tomorrow it may rain. And the sun will come from west. It is an impossible. These are some of the cases what we talk about in terms of probability. In other words, with the help of probability, we can assign a measure to the uncertainty with the occurrence of each possible outcome of a random experiment. What is the probability of getting a red card from a pack of red cards? Now the question arises, how many total cards are there? If we are simply asking about red cards, so we are aware of that in pack of cards, there are 26 red cards and 26 black cards. Going back to the basic formula for probability, that is total number of favorable cases. If we talk for the red card, 26 red cards, and total cards are 50. In that case, a probability of getting a red card from a pack of cards will be 26 by 52, which is 1. Now, because since we have to evaluate numericals as well as interpretation of the data. We should be aware of some specific terminology such as experiments, sample space, event, because these terms will be used in the problem. What is experiment? The term experiment is used in probability theory in a much broader sense than in physics or chemistry. Any action, whether it is tossing of a coin or measurement of a product's damage to ascertain quality or the launching of a new product in the market, constitutes an experiment in the probability theory term. Then comes sample space. The set of all possible outcomes of an experiment is defined as sample space. Each outcome is thus visualized as a sample point in the sample space. Taking up an example of the point, there are two outcomes, either head or a tail. That means sample space will be DH, event. An event in probability theory constitutes one or more possible outcomes of an experiment. Thus, an experiment can be defined as a subset of sample space. Experiment is toss of a coin. Sample space is D or H. Event is getting tail on head on the nose. What is the exact, or what we can say that what is the definition? Probability can be defined in two ways. First one is classical definition of the probability, and the second one is axiomatic definition of probability. Before defining probabilities, several other definitions need to be understood. What is random experiment? An experiment or trial whose outcome is not perfectly predicted, but for which the set of all possible outcomes is repeated. Trial is that is toss of a coin. Outcome will be either head or a tail. Then comes your random variable. A random variable is an assignment of numbers to possible outcomes of a random experiment. For example, we consider tossing of two coins. That means in that case, we have to find out number of heads. When the two coins lands on the coin. In that case, let the number of tails be t. The random variable assigns the number 0 to the outcome of tt. The number 1 to the outcome dh, because in that case, one head is there, and number 2 when two heads. Then comes outcome, space, and events. The outcome space is the set of all possible outcomes of a given random experiment. The outcome space is denoted by capital S. An event is a subset of outcome space. An event is determined by random variable. Outcome are the set of all possible results of a random experiment. Exhaustive events. Exhaustive events are a set of events in a sample space such that one of them will compulsorily occur while performing the experiment. That is, we can say that all the possible events in a sample space of an experiment constitutes exhaustive events. For example, by tossing an unbiased coin, there are two possible outcomes, either a head or a tail. If these two outcomes are exhaustive, as one of them will definitely occur while flipping the coin, and won't stand straight. Then comes disjoint or mutually exclusive. Two events are disjoint or mutually exclusive if the occurrence of one is incompatible with the occurrence of one. That is, if they can't both happen at once, if they have no outcome in common. Equivalently, two events are disjoint if their intersection is empty space. If nothing is common in between them. Independent event. Two events A and B are statistically independent. if the chance that both may happen simultaneously in the product of chances that each occurs individually. Our knowledge that one event has occurred does not give any information about whether other event has occurred too. For example, getting head on the first throw and getting head on the second throw are two independent events because the two points are equally likely events. Two events are said to be equally likely if the occurrence of one of them is expected in the preference to others. Equally likely events are those events which have an equal probability of occurring. That is, flipping of a coin, we can get either head, whose probability is 1 by 2, and tail, again 1 by 2. It is an example of equally likely. When we roll a die, the total probability of getting 1 is 1 by 6 because there are 6 numbers. And for 2, again 1 by 6. For 3, again 1 by 6. That means all these events are equally likely events. However, the probability of drawing one red ball in a bag of 3 blue and 2 red balls is 2 by 5. We're getting red ball. One red ball from bag. A bag consists of total 5 balls, and the probability of drawing a red ball will be 2 by 5. And the probability of drawing a blue ball from a bag of 3 blue and 2 red balls will be 3 by 5. We can clearly see that these events are not equally likely. Mathematical definition of if n is the number of equally likely, mutually exclusive, and exhaustive outcome of a random experiment, out of which m outcomes are favorable to the occurrence of an event A, then the probability that A occurs, which is denoted by P within bracket A, and mathematically it is written as number of outcomes favorable to A divided by total number of exhaustive outcomes. In this case, we have taken as n by n. All these approaches, however, share the same basic axioms. These axioms are fundamental to probability theory and provide us with unified approach of probability. The axioms are the probability of an event A, which is written as PA, must be a number between 0 and 1. Both numbers are inclusive. That means probability of any event will mathematically be 0 less than PA less than 1. That means probability of event will always be between 0 and 1. The probability of occurrence of one of the other of all possible events is equal to 1. If S denotes the sample space of set of all possible events, then we can write probability of S equal to 1. In tossing a coin once, probability of head or tail will be 2. If two events are such that occurrence of one implies that the other cannot occur, then the probability that either one or other will occur is equal to sum of the individual probability. That means probability of head plus probability of tail. When you are going to add up, will be 1. You know that probability of getting head is 1 by 2. Probability of getting tail is again 1 by 2. When we are going to add, we are going to get 2. Now, basic concept of probability, that is axioms of probability. We are aware of that all the concepts are divided by axioms. We are aware that probability of event is a non-negative real number, which is between 0 and 1. Both 0 and 1 are inclusive. Number 2, PS is equal to 1. That means when we are writing up the sample space, it is 1. There are few theorems on probability which will help you in mathematical treatment of the subject of probability. Here what we normally use directly in the number. Probability of no event is equal to 0, that is null. Probability of complement, B A bar, is equal to 1 minus probability of A, where A bar is the complement of A. That is rather we can say the negative part. For any two events A and B in sample space A, B A complementary intersection B is equal to PB minus B A intersection B. And if for the addition of probabilities, if we are having two events A and B, then A union B will be equal to BA plus PB minus BA intersection B. Then comes your conditional probability theorem. For any two events in sample space S, the probability of their simultaneous occurrence is given by PA intersection B is equal to PB PA times probability PA by B. You see it, how it is evaluated. Then comes your multiplicative theorem. That means that is intersection. PA intersection B is equal to PB PA into PB. This is one of the most important theory which is used practically by in the industry. That is based. Before starting the theorem, it is imperative to know about prior and posterior probabilities. Prior probability are those probabilities which are assigned to events on the basis of condition, that is the past experience or judgment. And posterior probabilities are the revised probabilities in the light of some additional information. That means some additional information will be provided to you. There you can say that this is a case of testing. It states that if A and B are two mutually exclusive and collectively exhaustive events, and C is another event defined in the context of same experiment, then if we have to, first of all, we have to evaluate BA, PB, BC by A, BCB by A, and mathematically it is evaluated as conditional probability is evaluated as BA by C is equal to BC by A into PA upon summation of both. And similarly, if we have to evaluate PB by C, you can see the difference that in the numerator, C by B is there and probability of B is there. The denominator remains the same. By taking up an example, we will see to it how it is evaluated. Now, a car manufacturing factory has two plants, X and Y. Plant X manufactures 70% of the cars and plant Y manufactures 30%. Total is 100%. 80% cars of plant X and 90% of the cars of Y are rated to be of standard quality. A car is chosen at random. It is found to be of standard quality. What is the probability that it came from plant X? We can assume that this is a very practical example. Now, mathematically, how with the terms of in terms of probability, how we will evaluate? How mathematically it is? E is the event that the car is of standard quality. We are talking about a car manufactured by any plant, first of all, but it should be of standard quality. That means, first of all, we have to represent event. Event is the car is of standard quality. Now, B1 and B2, here we have taken that car B1 is manufactured by plant X and B2 is manufactured by Y. Now, what is the probability of getting a standard car for plant 1? That means we manufacture 70% car from X to 70 by 100, total is 100. It comes out to be 7 by 10. Similarly, B2 will be 3 by 10. Now, second condition is 80% of cars of plant X and 90% of the cars of plant Y are rated at standard quality. Now, second part will be our basic problem is of standard quality. That is, we are talking in terms of standard quality. So it will be denoted by a car with standard quality from plant 1. It is 80 by 100. Similarly, car of standard quality from plant B. That is B2. That is 90 by 100. Now, all the data is given to us, and how the final part will be evaluated. What is the probability that it came from plant X? Mathematically, we have solved. That's fine. One thing you have to keep in mind that while solving the related problems to base theory, try to make denominator same everywhere. In B1, B1, you can see it is 7 by 10. B2, it is 3 by 10. In E by B1, it is 8 by 10. It has been reduced. And or reduced or rather simplified. E by B2 is 9 by 10. That means here everywhere the denominator is. Now, we have to evaluate that the car what we have chosen has come from plant X. So in the numerator, we will be talking about all the probabilities of plant. That means selecting a car from plant EB1 multiplied by the cars of standard quality divided and car is of standard quality and is of plant 1. It is PE by B. And in the denominator, we will be adding all the possible numbers. So after evaluation, we can see that probability of a car selected, car of standard quality selected from plant 1 is 7 by 8 times 8 by 10 divided by 7 by 8 into that comes out to be 56 by 83. Now, similarly in this problem, if the question is that the probability that it has came from plant Y, what we will change? We will simply change the numerator. Numerator, that means 7 by 8, 7 by 10 and 8 by 10 will be replaced by 3 by 10 and 9 by 10. And the answer can be evaluated. Then we move to unit 6, that is discrete probability distribution. Here, we will be finding out the probability of each experiment. If all the possible outcomes of an experiment, together with their chances of occurrence, are made. If getting on heads, you find that a toss of 3 points may result in 0, 1, 2, or 3 heads. That means when we are flipping up a coin and we are flipping up 3 coins, there is a probability that no head comes, 1 head comes, 2 head comes, or 3 head comes. So we have different probabilities. This representation of all possible outcomes and their probability is known as probability distribution. Suppose you are interested in number of heads in a tossing of 12 coins. You need to apply a discrete probability distribution. Discrete probability distribution can be used in decision making. If you remember, the last unit is related to decision. Outcome of toss of 3 coins were expressed in terms of number of heads denoted by H. So here, what H can take value? No head, 1 head, 2 head, or 3 heads. And correspondingly, we have probability associated. This uncertain real variable H, which assumes different value depending on the outcomes of an experiment, and to each of whose value a probability assignment can be made, is known as random variable. A discrete probability distribution counts occurrences that have countable or finite outcomes. This is in contrast to a continuous distribution, where outcome can fall anywhere in the company. Common example of discrete distribution includes binomial, Poisson, and Bernoulli's distribution. These 3 distributions are used in making management decisions. A discrete probability distribution functions have 2 characteristics. Each probability is between 0 and 1, inclusive, and the sum of the probabilities is, what does that mean? This statement, what does it mean? Sum of the probabilities is, if we toss a coin, we have 2 outcomes, either head or tail. The respective probability is 1 by 2 and 1 by 2. When we add 1 by 2 and 1 by 2, we are getting, that means the sum of individual probability. While doing mathematical calculation, remember that the outcome of all the probabilities sum should be 1. Discrete events are those with a finite number of outcomes, that is tossing dice or coins. For example, when we flip a coin, there are only two possible outcomes, right? When we roll a six-sided die, we can get any number between 1 to 6. In that case, mean can be evaluated summation of x into bx. The variance sigma square and standard deviation sigma of a discrete random variable x are numbers that indicates the variability of x over numerous trials of experiment. Again, we will be evaluating this value. Now you can see how it is written. Probability distribution of number of x. We said that no head, 1 head, 2 head, 3. These numbers 1 to 0, 1 to 3 are discrete values. And probability of getting a head. This is in terms of 3 points. Respective probability is given. When you find this pH is the probability distribution. The random variable is number of heads. When you are going to add these numbers, you are going to get probability distribution of a random variable. A description given the value of random variable along with corresponding probabilities is called probability distribution of random variable. You can see over here, random variable are from x. For x, takes the value of x1, x2 till xn, and the respective probabilities will be p1, p2 till pn. Mathematically, it is written like this. Now, how computation of things are. This above probability distribution of x is defined only when each p1 is greater than 0 and all the summation of pi from 1 to n is equal to 1. Now we have discussed about 3 things: mean, variance, and standard deviation. You will see how they are evaluated. We talk in terms of mean. It is denoted by mu, which is equal to ex, which is equal to summation of the product of xi and pi. And if we talk for variance, it is summation of xi square pi minus mu square. That means square of the mean. And the standard deviation is under root of variance. We will see when we find the mean, variance, and standard deviation of number of x when 3 points are tossed. Sample space, all the possible spaces are given to you: TTT, TTH, THT, HTT, THH, HDH, HHT. These are the 8 outcomes. The NS will be equal to possible outcomes. We are talking about toss of head, getting head. Head, no head, 1 head, 2 head, or 3 head. Now you can see how evaluation is done for getting probability of no head. So similarly, we can see to the sample space. There is only one condition from the 8 which does not have any head. That is, all the 3 outcomes are tails. That is 1 by 8. If we talk for 1 head, so there are 3 events where head is there. That is 3 by 8. And if we talk for 2 heads, again there are 3 events where 2 heads are there. That is 3 by 8. And for the 3 heads, it is 1 by 8. When we are adding up, we are getting 1. 1 by 8 plus 3 by 8 plus 3 by 8 plus 1 by 8. When we are adding up the numerators, we are getting 1 plus 3, 4, 4 plus 3, 7, 7 plus 1, 8. 8 by 8 is 1. That is mathematically it is correct. Now we have to evaluate mu. That is, mu is equal to summation xi pi. Multiply 0 by 1 by 8 plus 1 by 1 into 3 by 8 plus 2 into 3 by 8 plus 3 into 1 by 8, which comes out to be 2 by 2. Now we have to evaluate summation x square. into pi. So first of all, we will be squaring x and multiplying by 1 by 8. You can see that 0 into 1 by 8 plus 1 into 3 by 8 plus 4 into 3 by 8 plus 9 into 1 by 8 minus mean square. Mean is 3 by 2. That comes up to the 9 by 4. After evaluation, we get 3 by 4. And standard deviation is under root of 3 by 4, which comes up to be root 3 by 2. Now, the second part is Bernoulli's theorem. We have a mathematical relation and we have to use combination theory over here. Let there be an independent trial in an experiment and let the random variable x denotes the number of successes in that trial. We are aware of that probability of success is denoted by P and the probability of failure is denoted by Q, and probability of success plus probability of failure is equal to 1. For getting at the output of the what we call it as Px, we have a relation for evaluating it, which is equal to NCR P raised to the power R times Q raised to the power N minus R. Now the question is how to evaluate NCR. NCR is equal to N factorial upon R factorial into N minus R factorial. Now the thing is that how this table will be generated. We have to take x is equal to 0, 1, 2, 3 till R. Similarly, we will be placing this in this form. Px, if 0, we have to take probability of failure raised to the power n, the number of times the event is. This representation is for the binomial distribution. Now the thing is that there are typical examples where this is used. Coin tossing and success failure situations. That means depending upon the situation, we have to use the relation. Conditions for the application of binomial distribution. The experiment is performed with fixed number of trials and is performed for finite trials. The numbers are, it cannot be said that till win occurs. It has specific number. Each trial must be either a success or a failure. And the probability of success in each trial is for evaluation of mean, variance, and standard deviation under binomial distribution. So we have mean is equal to n times p, variance is equal to sigma square is equal to npq, standard deviation is the under root of variance. Then comes Poisson process and distribution. Poisson distribution is applicable to events occurring randomly over time and space. Repeated distribution of several random variables like to count the number of defects of a finished product. See the examples where it is to count the number of deaths in a country by any disease or natural calamity, to count the number of infected plants in the food, to count the number of bacteria in the organism or the radioactive decay in atoms, or to evaluate the waiting time between two events. Depending upon the nature, we have to evaluate which distribution has to be. For that again, we have a relation. Poisson process corresponds to Bernoulli's process with a very large number of trials and a very low probability of success. In that case, we can take this up as m or lambda is equal to np, where r is the number of success. So for evaluation, we will be using this relation. Pr is equal to e raised to the power minus n times m raised to the power r upon r factor. What are the properties of Poisson distribution? The events are independent. The average number of successes in given period of time alone can occur. No two events can occur at the same time. And The Poisson distribution is limited when the number of plies n is indefinitely large. Here we take up a value. We assume that mean and variance is equal to lambda or n, which is equal to the product of n, which is finite. The standard deviation is always equal to square root of its mean. That is mean. With this, I will be concluding today's session.